heard the announcements. Can't think of anything new there. I guess we're ready to go then as soon as we can get projection going. Where we left off last time, were there any questions? Huh?
Not on the last time, we did have a question on the test.
Okay.
Just on number 1 where it's EDX 5 plus C1 E with negative 2A.
Right.
Is that just asking for the derivative?
Just take a derivative, that's all.
I was just making sure. I was like, maybe
Okay.
there's something more to that?
Nope, that's it.
It seems to.
Yeah, I know. But they had, they had it in the material they had. And I thought, well, I'll start with something really easy then.
Okay.
And by the way, they had the answer wrong in their key.
Really?
Yes.
No way.
I couldn't believe it. I think it was just a typo, but it was amazing. Okay. Any other questions? Either test or otherwise. Okay. I think we got projection now. It finished pretty much 2.3 except on the remarks, which usually I avoid, but when they're talking about these functions, there are some names that are associated with them, and I just wanted to share some of those with you because you might run into these. Mathematicians have adopted as their own, this is on page 62, remarks, Roman numeral 2i, little I. Mathematicians have adopted as their own certain words from engineering which they found appropriately descriptive. One of these words I think we've mentioned before is transient. Let me get my pen set up. Well, I can't get my pen set up. There it goes. Okay. Transient. I can't spell. Okay. Remember when we had some function in e to the minus something another, the transient function was, it'll vary for small e's, but then when you get to large e's, the e to the minus something disappears. So that's one. That was used earlier, one of those terms. Sometimes in future discussions, they're going to talk about input and output. And quite often I think of that as domain and range, what you put in, what you get out. Sometimes it's a little more complicated than that, so we'll see that coming up. If you go back to their example 2, way at the first of the section, not example 2, equation 2. Okay, when you had dy dx, this is a linear function, dy dx, that's an ugly dx, isn't it? Excuse me, plus p of xy is equal to f of x. Our standard standard form for your linear equation, okay? This is sometimes called the input, okay? And then another word for it is driving function, okay? What drives the output, basically. Then the solution is the output or response. Y output or response. Which isn't quite input output like we did for domain and range. Usually the x would be the input of that. Here's the f of x. That's the driving thing. And then what you get when you, after you solve this, the y is in the output of the response. Okay? And then they do a couple on some special functions, the error function, sine integral function, Fresnel sine integral function. I'm not going to do any more with that. If you think in your area of study or interest, that's going to be something that's important. Please pursue it. If you have questions about it, I'll be glad to try to dig through those with you, but those are ones I've dealt with them, and as far as being in class with them and talking about them, never have used them. And I don't even have a real good idea what they're used for. So, I don't know. So, anyway, that finished up 2.3. Any questions? Let's go now to 2.4. So let me erase all that. Now, here is another sort of simple looking first order differential equation. Y dx plus x dy is equal to 0. Indeed, that is a pretty simple thing. We usually don't write them that way. What we normally would do with this is subtract the y dx from both sides. Okay. Okay. And you have x dy is equal to minus y dx. And then you would divide both sides by, or not write that in differential form, put it over dx, and then divide by x. dy dx is equal to minus y over x. Which you could write this way, dy dx plus 1 over xy is equal to 0. That's linear form, right? Okay. And you can do with that, this is a real easy thing. It's your p of x, integrate it, you get a log, it, it comes out pretty simple. I've never used it so much as in this class. It just seems like a good way to express it, since y'all know what I'm talking about. Okay? They say here it's both separable and linear. I've just shown you how it's linear. I didn't show you how it's separable. It was already set up to be separable to begin with. Let's go to this step here. X dy is equal to minus y dx, and divide both sides by x and y. And here your x's go out, and this gives you log y is equal to, here your y's go out, minus log x. And then you can have a plus c if you want to. I think I'd put it as plus cx. God, can't say what I'm trying to say. I can't even. Log c is what I was trying to write, and I couldn't even get it said properly. Log c, and this would be log y is equal to, let's see, minus that's not quite the same, but then e both sides and you get y is equal to minus cx, or c. Let's see how they say that. This
but when you did the C there,
yeah.
you took the natural log given y e to the c.
Yeah.
Shouldn't you have changed that c to another kind?
Yeah, you should. Yeah, I'm not doing it properly. I'm just saying it's some constant. That's what I'm setting for. But I was starting to carry it further, but really you don't need it any further. It's the point is, you can solve it both of the ways we've done. Separation of variables and linear. I didn't want to necessarily carry it all the way. They say this is the perfect derivative of, and then yet another way is this, that this is a perfect derivative of xy, because when you differentiate xy, you get x dy plus y dx, right? And that's exactly what you've got there in the reverse order. But then, you know, there's lots of other things you can do with it. I mean, but what we're getting at, I'm not sure why they went to all that length on that one, but here's what they're getting at. In this section, we examine first-order different equations written in differential form, and generally they're going to be like this. M of xy dx plus n of xy dy is equal to 0. Now the key is equal to 0, okay? It said by applying a simple test to the coefficients m and n, we can determine whether this form here that we got here is a differential of a function f of xy. If the answer is yes, then we can construct f by partial integration. Now this is the part that we're ahead of Cal 3. In fact, it's what we're going to do next chapter. You know, when we start next chapter, we're going to be doing what we're now going to be doing here. So this is where you're taking this course is getting a little bit ahead of, because you didn't have the prerequisite course. Okay? Now, because we haven't talked about partial integration yet, certainly either. We haven't even talked about partial derivatives. So we'll get to it as we need to, okay? Now, let's just say we have some, how I managed to do that, okay. We have some function, z is equal to some function of x and y, okay? Two variables with continuous first partial derivatives in some region R of the xy plane. Now, this is what you haven't had yet, and let me explain it to you. Okay. Here we have a dependent variable z, depends on two independent variables x, y. We haven't done that in calculus. Y'all have it. I know we have it in calculus, but have you run into it before in the test? Okay. Probably not, because that's what we're going to hit in the next chapter. And Cal 3. Okay? Here is a true statement. Okay. If you do the derivative of this z, what you're doing, this is called writing this in its differential form. And just take my word for it now. It's the partial of f with respect to x dx plus the partial of f with respect to y dy. Okay? Now, if you think about this, this almost looks like, okay, z is f of x, so f of xy. Okay, partial of z then should be sort of like, the derivative of z should sort of be like the derivative of x, except there's two variables there, okay? But this looks like these would cancel out df, and that would be df. So in a sense, it looks like dz would be the same as df. Now, sure, you might say that's 2df, but not really. Don't worry about that. Okay. Now, what do we mean by a partial? Those funny-looking symbols there. When you're taking the partial of a function, a partial that's a function of two or more variables, and you're taking it with respect to one of the variables, you treat the other variables for this purpose only as if they're constants, and only take the derivative with respect to that variable. So this one, then we'd only take the derivative of f with respect to y, not with respect to the x's, okay? And then this form is your differential form, or a function of two or more variables. If you have more variables, just keep on trying. You just do the partial of each one. Okay. Now, if this f of xy, okay, happens to be a zero, no, I'm sorry, happens to be a constant, okay? If that happens to be a constant, okay, c is any constant, then this partial with respect to z, if z is a constant, that partial is 0, because the derivative of a constant is 0. Okay? Now we get a form that looks like this. Okay? All right. This is sort of, it's manipulating to try to get you into a form where you need to go. Okay? So in other words, given a one-parameter family of functions, f of xy is equal to some constant c. Okay? We can generate a first-order differential equation by computing the differential on both sides of the equality. Okay? Let's do it here first. The partial of f with respect to x dx plus the partial of f with respect to y dy is equal to 0. If this is that, and this is that, then we have something we can differentiate. Okay? That's what we're getting at. Okay? Now, in other words, if you had a one-parameter family, okay, we generate first-order differential equations by computing the differential on both sides. So let's take an actual example. Not an example from the text, but what they use as an example in the text. Okay? What if we had this? X squared minus 5xy plus y cubed is equal to some constant c. Okay? Now we're kind of doing things backwards here. I don't see a differential equation there, but what we're doing is showing, if you started with this and took a derivative, how you can make a differential equation, then you can undo that and get back to here again. That's sort of a kind of a backwards way of doing it, but that's what we're going to do. Okay? So what we want to do is the partial of this thing, x squared minus 5xy plus y cubed, with respect to x dx, plus the partial with respect to y of x squared minus 5xy plus y cubed is equal to, and the derivative of c is 0. Okay. Now, like I just told you, let's take the partial with respect to x, with respect to this variable x, counting all the other any other variable as if it's a constant, and of course all the constants are constant. So let's do it first. What's the derivative of x squared? 2x minus, what's the derivative of 5xy with respect to x? Minus 5y. Perfect. And the derivative of y cubed with respect to x? 0. You got it. So you get this dx plus, and let's do the same, but this time with respect to y, Derivative of x squared with respect to y? 0. Derivative of negative 5xy with respect to y? Negative 5x. Okay. And derivative of y cubed with 3y squared. Oops. dy. Okay. So here we have the differential equation. Okay. This is our m of xy dx plus n of xy dy is equal to 0. That's the form we had at the beginning, and this is in differential form. Now, hey, you answer me this. Would this benefit us in trying to get this as dy dx as some function of x and y? No. I don't think there's any way you would be able to manipulate that to get it into a linear or separable or any other kind of equation. Okay? So basically what we're going to do is try to deal with an equation that looks like this. Now we already know the answer. It's written right up there. You know, it's a one-parameter system, but it's not a, you can't write it explicitly in terms of y, or it would be very difficult. I don't think you can at all, or in terms of x, so you just basically, that's your solution for this differential equation. And that c is your one parameter. Okay. Now, a little definition here. Of course, not every first-order differential equation written in a form like this corresponds to an f of xy equal to a constant. It just doesn't. Don't imagine it could. So for our purposes, it's more important to turn the foregoing example around, namely, if we're given this is a differential equation, how do we find its solution? Okay? Is there some way to recognize that the differential expression is a differential of that? If there is, then an implicit solution is that, what we have there. So here's the definition. I'm going to start with a clean slate here because this is a wordy definition. Okay? A differential equation, DE is differential equation, a differential expression. Okay. Maybe I should write it. D stands for differential. Differential expression. It may not, well, I mean it. Okay. A differential expression, m of xy dx plus n of xy dy. Now, it's not set equal to anything, but that differential expression is called an exact differential. Okay, exact differential in some region R, okay, of the xy plane okay, if it corresponds to the differential of some function, the perfect differential okay, of some function f of xy. Okay, we're only dealing with two dimensions, xy plane, okay, defined in R. Also defined in R. Okay. A first-order differential equation of the form m of xy dx plus n of xy dy equals 0 is said to be an exact equation if the expression is an exact differential. If the left-hand side is an exact differential. Okay. Okay, if that m of xy dx plus n of xy dy is an exact differential. Okay. Now, here's a couple more examples. For example, not example to work on, but just example. X squared y cubed dx plus x cubed y squared dy equals 0 is an exact equation. Now, this one you can almost look at and tell. Okay? Looks like this has had one derivative taken, doesn't it? If that had been an x cubed to begin with, take the partial of this with respect to x, you get 3x cubed y cubed. Take that same thing and take the partial of this with respect to y, you get 3x cubed y squared. So divide everything by 3 and you get a 1/3 there. So this would be an exact differential of 1/3 x cubed y cubed. Now that was easy because it was so, almost obvious. Okay? That would be equal to that thing up there, the left-hand side. Okay? So, what you could say then, okay, the next sentence really, okay, it says here, Theorem 2.4.1, given next, shows that the equality of the partial derivatives is no coincidence. Okay? Oh, okay, I'm sorry, I skipped something. Okay. Notice that if we make this identification, and this is a key, it's coming up next. They're showing us now, giving us the theorem in a minute. Okay. Now, remember this was some partial of, it's on the previous slides that I've already erased. This is a partial of this thing with respect to x. That's the partial of this thing with respect to y. Well, with maybe a constant in there. So here's something to note. What if we took the partial of this thing with respect to the other variable? Partial of x squared y cubed, but took that with respect to y. What would that give us? Three x squared y squared. You're absolutely right. Now let's do the same thing to this one, but take with respect to the other variable. The partial of x cubed y squared with respect to x, because this was the partial of this thing down here with respect to y, but let's do it with respect to x. What do you get? 3x squared y squared, exactly equal. All right. Now that's just not a coincidence, that's a test, okay? And here's what the theorem tells us we can do, okay? Seems like we've set it up to do this, and in a sense we have. If you let m of xy and n of xy be continuous and have continuous first partial derivatives. They themselves have to be continuous and have continuous first partial derivative. PD is partial derivatives. Okay? In a rectangular region, R. They're going to define the R. Okay? Defined by A is less than X is less than B, and C is less than Y is less than D. Okay, between A and B on X, C and D on Y. Then a necessary and sufficient. I can't spell, but there it is. Sufficient condition that m of xy dx plus n of xy dy is equal to 0 . Then a notion that B, and it sounds strange, but that's the right verbiage, be an exact differential is, here's the requirement, necessary and sufficient condition for that to be an exact differential. Okay, I'm sorry. If you put the equal, it would be the exact differential equation, not equal to 0, just that exact differential. If partial of m with respect to y is equal to partial of n with respect to x. You just take the partial with respect to the opposite variable of what follows it. And if those two are equal, then you have an exact differential. Okay. All right, now they go into the proof for the necessity part. The sufficiency part consists of showing there exists a function for which blah blah holds. The construction of that function actually reflects a basic procedure for solving differential equations. So let's just leave it there. If that condition is met, then we can do an exact differential. Now, we haven't shown you how to do it. That's what's coming next. How do you get that solution? Okay. So, I'm going to start over on clean page, and let's go for it. Let's say we start with an equation, m of xy dx plus n of xy dy equals 0. Okay? Now, first thing you do is take the partial of m with respect to what? Y, and see if it's equal to the partial of n with respect to x. If yes, continue. If no, we'll stop now, but may not forever hold our peace. Okay? There may be something we can do. We'll talk about that later. Okay? So the first thing we do is check and make sure those are equal. Okay? Now, what that means, if those are indeed equal, if yes, this is where we go. That means there is some function f, okay, such that the partial of f with respect to x is equal to this m of x, y. Okay? Remember, that's where we first started. If there is that function, then the partial of it with respect to x will be the m of xy. Okay? Now, here's what we do. And this, again, is getting somewhere you haven't gone before but just hang with me. Let's write that in sort of differential form, except I'm going to go on and make it df is equal to m of xy dx. Okay? Now, how could I get away with that? We're keeping the y's constant. And when you keep the y constant, you can write it as a derivative rather than a partial derivative. Just going to keep the y's constant. So by doing that, we then integrate both sides. You integrate a perfect derivative and you get f of xy. Now, we're only interested in the x part now, okay? You integrate this thing with respect to x. How do you do that? You integrate with respect to x, keeping y as constant, just treating the y's as if they were constant. Just the way you did it the other way when you took a derivative. Okay? Now, when you do that, normally, because this is an indefinite integral, you would put a plus, except now it's not a c. It's some function of y. So we put g of y. We don't know what it is, but we just put down some g of y. Because, you see, y's are all counted as constants, so we can't eliminate the y's, so it's some function of y. It can have constants in it, perfectly fine, and it may be itself only a constant, but it's we have to consider that it might have a y in it. Okay. Now, so this is what your f of xy is. The integral of, I'm sorry, gag. Of whatever you were given there to begin with, m of xy dx plus some constant, but some function g of y. Okay. Now, what we're going to do next is differentiate this with respect to y. Partial of f with respect to y. Okay? Now, you've integrated the x's out, so this is only a function of y. Whatever it is, we just don't know. And this is only a function of y. So, all I can do for this is write it as partial with respect to y. Actually, that's of m of the integral of m of xy dx. Okay, just treat that there. Plus g prime of y. G has no x's in it, so it's just a derivative of y. Okay?
You're just doing the thing above that.
What's that?
You're just differentiating
With respect to y.
with respect to y.
Yeah. Of whatever this thing left off, it may have had x's in it. Certainly it's going to, I guess it still has y's in it. Take the derivative with respect to y. Partial with respect to y. Okay. Now, this partial of f with respect to y, though, remember that's what your n of x was. When we first set up, if there is a solution for this, which this says it is, then just like the partial with respect to x was m of xy, the partial with respect to y is n of xy. So now this thing that we have here is that n of xy. All right. Now, what we do at this point is solve for the g. We already know what m is. We hopefully know what its integral is. We hopefully have taken a derivative of that. So there's a lot of things we have done. We just can't show them now. And we know what n is. So now we say that the g prime of y is equal to n of xy minus the derivative, partial with respect to y, of the integral of m of xy dx. Okay. Now, guess what, folks? It's not this complicated. It looks terrible here because we haven't taken a single derivative and done a single integral. But this just turns out to be some function that you can take a derivative of. And this is just some function you have to begin with. So don't let it freak you, okay? But this is your, what G prime is, okay? Now, this is dg, and this is a perfect derivative, is a derivative. Well, multiply by dy and integrate both sides. I already did the integral there. This gives you your g, and this gives you whatever that is. The integral of n of xy minus derivative, and this is all in parentheses, derivative with respect to y of the integral of m of xy dx dy. Okay. Now, what a mess. What an incredibly ugly mess that seems to be. Okay? Except for this. Oops. If we broke off and did a dy here, and then put another integral sign there, that would be okay. And it's getting so crowded, it's hard to see what's actually coming out of this. But whatever you get here for this g, you go back up here. Remember, you've already evaluated what that is. You come back up here and plug this in here, okay? And then you've got your answer. Except, don't ever put a plus c out here or something. Once you put these together, remember f of xy is equal to c. So you plug this thing back in here, and then do this plus that is equal to c. You don't have integrals in there anymore. You don't have any derivatives. You've already done all those things, but that gives you your function. Okay? Now, it says some observation of order. First, it is important to realize the expression n of xy minus the partial of that is independent of x. Okay? It's this thing right here. This thing right here. You've integrated out the x there. So this partial with respect to y, I think, could be a derivative with respect to y. Okay? You've integrated that. That's not completely true, but let's do it. There is a thing here that we if you were to go back to this expression here, and let me delete some of my lines from before because they are sort of messing up things. Okay, let me not delete too much though. This thing right here, I can't get my pen back. Okay, this thing right here, well, that thing there. Without the integral sign, sorry. Without the integral sign. Okay? So, let me take the integral off and the dy off. Put the integral on the outside and the dy on the outside. Okay. Okay. That thing right there. Okay. They're saying this has no x dependence in it. Now, it's hard for me to see because that says it has x dependence. Okay? But if you were to take the partial of this, like we did up here with respect to x, and the partial of this with respect to y, the partial, with respect to y, no, I'm sorry, you don't need to do that. Just the partial of this thing with respect to x. Okay? Okay. In both of these. Okay. Partial of this with respect to x minus partial of this with respect to x. Right? Now, you can, there's another thing you don't know yet. You can exchange the partials. Because they're continuous functions with continuous partial derivatives. You can't exchange them. So you can move and flip this. Well, then this thing becomes, if you take the partial of this with respect to x, the partial of this with respect to x, and flip these two, then you have the y, partial with respect to y, partial with respect to x. This thing is just L of x. Because if you take the partial of an integral with respect to the same thing, you lose it. Fundamental theorem of calculus, part 1, I believe it is. No, part 2. Okay? Take the partial of this with respect to x dx. You lose the partial undoes the integral together. So now you have partial of this with respect to x minus partial of this with respect to y, and guess what? Those are equal to 0. Okay? So we're using our test here, and sure enough, then that thing, the whole thing together, even though this still may have some x's in it, this has some x's in it, the partial of that is going to 0. The dependence of that goes to 0 because they wipe out each other out. Okay, basically as a consequence of that. Okay, so wow. That's the first thing they say, note. The second, we do just as well to start the foregoing process with the assumption, rather here that the partial of F with respect to x is m of xy. You could have started down here and said the partial of F with respect to y is n of xy, and done it that way. So basically, what it says, if one way gets really nasty, try it the other way. And if that's a lot easier, go with that way. Either one of them should work. And then the final thing. In either case, none of these formulas should be memorized. Please don't. They're too complicated, too easy to forget something in them. It's the procedure that you do, not filling in a formula. Okay, so let's actually do one. Okay? And this one, thank goodness, we'll actually be able to do. So here, what we have. 2xy, goodness gracious, I say y and write a d because I know that's coming next. Okay, 2xy, I'll get it right one of these times. Okay, 2xy dx plus x squared minus 1 dy is equal to 0. Now we don't know for sure, but how can we tell if that's an exact differential or not? What's our test? 2xy with respect to y, and see if that's equal to the partial of x squared minus 1 with respect to x. Well, what's the partial of 2xy with respect to y? 2x. And what's the partial of? That's 2x also. Ding, ding. It works. So therefore, we know this is an exact differential. So let's start. Okay? Can I go on and erase that? Because hopefully we may need the room, and I don't want that to be in the way. We've just confirmed they're true. Okay? So rather than let this muck up what we're going to do later, let's see what we got. Okay. Where do you want to begin? Okay. Since it is an exact differential, that means there is some function, f of xy, equal to c, that satisfies that this differential equation satisfies. It satisfies that differential equation. Let me put it that way. Okay? That's the given here. Since that test worked, we know there is an f. So where do you want to begin? Partial of f xy with respect to which? With respect to x, that's going to be equal to what then? M, which is 2xy. Perfect. Now, treat it as if those were derivatives, not partials, and you're going to integrate the derivative of f, I'll just do it that way, dx, no, just, I'm sorry, df. We don't need another d in there. Okay. Okay. And that would be equal to the integral of 2xy dx. Okay, so this just gives you f of xy is equal to what? It's the antiderivative of 2xy with respect to x only. X squared y plus second g of y. Some other function of y alone. No more x's, y alone. Okay? Now, what do we do next? Take the partial of this with respect to y. Okay? Is that right? Am I skipping a step too soon? Yeah. Okay. And that, you know, is partial of this f, which is this thing here, is n of xy. Right? Okay. So, let's take the partial of this with respect to y. What would that be? X squared plus g prime of y is equal to x squared minus 1. Right? That was your n of xy. Yay? Okay. Now, let's solve for this. So, g prime of y is equal to x squared minus 1 minus x squared. Uh-oh. G prime of y is equal to negative 1. Could it be? If that's true, then that means dg dy is equal to minus 1, which means dg is equal to minus dy, right? Yay or nay? Okay. Integrate both of those, and what you get? G is equal to negative y. Okay? I'll take this and plug back into this form, which I've almost lost here. F of xy is equal to x squared y minus y. And that's equal to some constant c. That's not a 0, that's a c. There is your f of xy is not your solution. This is your solution. X squared y minus y is equal to c. Now this one we happen to be able to solve explicitly in terms of y, because we could factor out a y here of x squared minus 1 is equal to c, and this would then be y is equal to c over x squared minus 1. Okay? Both of those are solutions. You don't put the f of xy anymore. That was just there to hang on to it. That thing equal to c, that's your solution, or express it explicitly in terms of y, that's your solution. Now, remember always it said within some region R. Can you tell any restrictions you may have on that region R? R is defined as, yes, you cannot have x equal either plus 1 or minus 1. So either x is going to be less than minus 1, between minus and plus 1, or to the right of plus 1. So 3 different places that region could be, but it can't ever contain either a plus 1 or a minus 1. So over here somewhere, over here somewhere, over there somewhere. So if you had an initial condition, that nails it where your function is defined.
Oh, he's not through. He's got to go some direction fields because he sees that big C up there.
Yeah.
Oh, he's got to make it complicated.
No, we're going to leave it right there. Going to leave it right there. You have to have the dy dx to do a direction field, because that's what the direction is. And let's not. Didn't say we did. Okay. So no, this is how we leave it. Is defined in any interval not containing either plus 1 or minus 1. Okay. So your solution is not f of xy. That's not your solution. That thing is equal to c. That is your solution. Do we have time for another one? I think so. They're not nearly as bad as the derivation. They work out much, much nicer than that. Okay, here's one. That other one was just way too easy, wasn't it? Okay, let's do this one. E to the 2y minus y cosine xy dx plus 2x e to the 2y minus x cosine y plus, no, cosine xy. It's beginning to look like a test problem, isn't it? Huh? Okay. Plus 2y dy equals 0. What if that was our differential equation? Certainly a differential equation. Anyone want to guess whether it might be separable or not? How could you figure that? You got a cosine xy in there. How are you?
Never mind. I didn't even notice that.
Okay, yeah. And
then the e to the 2x.
What's that?
2x e to the 2y. Yeah, never mind.
Yeah, that part would be separable, but that and then an x cosine xy and a y cosine xy and a x cosine xy, I don't think so. Okay. I don't believe so. Okay. Think it might be linear.
Oh, you've got cosine there, xy.
Yeah, they got cosine xy, e to the 2y. Nope. Not going to be linear. So the only hope we have right now so far is we hope this is exact. Any way to tell if it's exact or not? Yeah, of e to the 2y minus y cosine xy with respect to y. Let's see what that does. What does that become? 2 e to the 2y minus product rule y or not. Make that a plus. Sine xy times x. Okay? All right, there's your product. There's the partial of that thing with respect to y. And then we do the partial of this thing with respect to x. 2x e to the 2y minus x cosine xy plus 2y. And what does that become? 2e to the 2y, is that what you said? Perfect. I thought it was. Okay. Here's the product rule again. Wait, did we ever do the second part of the product rule here?
Yes.
Yeah, I thought we didn't, did we? What were we missing?
Oh, you're right. Minus, yeah, cosine xy.
Okay. Yeah, we just did the first half of the product rule there. We left off the second half. Okay. Let's go back here now. Minus what? X. Only gonna make it a plus sign, right? XY. Y. So I got that. That's the first half. Cosine xy. With respect to x.
Oh, I'm sorry. Nothing.
0. Now looky here. Those are identical, aren't they? So indeed, they are equal. These are equal. Those are equal. So we can do it. All right. Now that we know we can do it, let me erase those. You okay? Okay. Didn't look very promising, did it? But it worked. All right. Now the question is, which one do we go for? Start it where it's... Okay. Now, here's the supposition. There is some f of xy, and we know there is now since those are equal. There's some f of xy that's equal to some constant c. Okay? And, given that, what's the partial of that f of xy? And it depends on you where we start it. With respect to x, then that would have to be e to the, this should be it, e to the 2y minus y cosine xy. Right? Okay? Now, do a dx here, integrate there, integrate there. So this gives us a f of xy is equal to what? That's just a constant. You're integrating with respect to x, so that's just a constant. So it'd just be x e to the 2y. That wasn't too bad. Ooh, but we hadn't got to the second part yet. But it's not too bad either, is it? The y is just a constant. That's the antiderivative of cosine. Yeah, and we'll leave that alone. So it'd be sine of xy, but we have to unchain rule it. That's a weird way to say it. You know, when we're taking a derivative, we multiply. When you're doing an antiderivative, you divide by the constant here, right? Y. Ooh, looky here. What else? One more thing. That's an indefinite integral. Hint, hint. Plus. Say again? No, it isn't. G of y, because you're integrating with respect to x, it could have a y in it. Yeah. Okay. Okay. Now, I'm going to leave that alone because last time I did it. So now what I'm going to do is take the derivative of this thing, but this time with respect to y. So let's do that. The partial with respect to y of this thing here, x e to the 2y minus sine xy plus g of y, and that needs to be n of xy, because the partial of the alpha is n of xy, which is 2x e to the 2y minus x cosine xy plus 2y. Okay, we'll get there in a minute. Let's take the partial of this first. What do you get? 2x e to the 2y. Okay? Minus cosine xy with an x in front. Got it? Plus g prime of y. You got it. And that's supposed to be equal to 2x e to the 2y minus x cosine xy plus 2y. I hope I wrote it right. Yeah, okay. Now, what do we want to do? Isolate your g prime, because we're going to undo it. So that means we're going to subtract the e to the 2x e to the 2y from both sides. I just did. And we'll also add x cosine xy to both sides. I just did. And what does that leave you with? G prime of y is equal to 2y. Well, let's rewrite this as dg dy is equal to that. So we'll take this and make a dy here. And the antiderivative of dg will be just g of y is equal to y squared. Don't put a plus c. Just leave it y squared. Okay? So we come up here, and instead of gy, we do y squared. All right? And then what we do, we set this thing, x e to the 2y, that's not a minus, that was where my pen set down what it wasn't supposed to. Minus sine of xy plus y squared is equal to c. Now, do you think you can express that as a function of y alone?
Yeah.
Oh, really? Let me watch you do
I don't
that.
know if it makes sense, but I can write it out.
I don't think so. You'd have a log from this term, and then you'd have an inverse sine from that term, and you can't do both of those. Yeah. Okay. I think that's going to be our answer. Let's check and see.
That is what that happened.
X e to the 2y minus sine xy plus y squared, and then for some reason they write it as plus c equals 0. There's no reason to do that. I don't know why they wrote the c on the other side. If you want to equal 0, you could. A minus e plus c, it doesn't matter. Okay. It's just a constant.
They did the whole thing with starting with the partial respect to y.
Oh, why would they do that?
I don't know.
It is no worse.
More to it for a little bit.
There's a little bit more, and so I think our way was just as simple. I think maybe a little bit simpler. Okay. All right. You can do it either way, though. Perfectly fine to do it either way. Now, most of the time they put the answer in blue, and this one they didn't. They just left it there at the top of page 68. And I think we have run out of time, haven't we? Sadly.
As fun as it was.
As much fun as it was, okay? Whoa! We came close to finishing 2.4 also.
So we made it, all that stuff equals C.
Right.
But then they did a plus C equals 0.
Well,
Wouldn't that be minus C?
okay. C is just a constant. Right. C is just a constant. We could have made that a minus C. That still would have been a constant. Then added that to both sides. We'd have looked just like that. It's whatever you put there. Like I said, I don't know why they did it that way here, but it's okay. Okay. Hey. All right. So let me, homework exercises here will be any of the odds that you can find in the back of the book, 1 through 19. And then any of the odds 21 to 25 that you can find in the back. Oh, no. Stop at 19, because the next example is your initial value problem. So we'll do that later. Just do any of the odds 1 through 19 that you can find in the back of the book. Okay? All right, good deal. So I'll shut this down. Any questions before I do?